Our objective is to understand a possible problem coming from delays in the amplifiers we apply feedback to and in the feedback network itself. No amplifier is truly without delay, because all amplifiers have capacitance and inductance. You may have noticed that our feedback block diagram employs uppercase signals with lowercase subscripts. This is because the signals are best analyzed in the frequency domain. Recall from phasor or Laplace transform lessons that the output in the frequency domain is the input multiplied by the transfer function. The entities A and beta are transfer functions. The entities we need to examine are xf and xi. The transfer function between them is the product of A and beta, and this product is known as the loop gain. Recall from phasors that the magnitude of the transfer function is how much the amplitude of an input sine wave is magnified, and the angle is how much the output is shifted along the t-axis relative to the input. Real amplifiers are causal, meaning the output doesn't change before the input does, which means real-world amplifiers have delay. Let's understand this better by looking at an example. Suppose the input to the loop is a sinusoid turned on at 0.2 seconds with a radiant frequency of 1. The magnitude of the loop gain is 4 and the delay is 3 pi over 4 seconds. Notice that the red output wave is 4 times the amplitude of the blue input wave. And also notice that the red output wave is delayed from the blue input wave by 3/4 pi seconds. Let's go back and look at the block diagram and think in general terms instead of for this specific example. If the signal source x sub s is removed just as the feedback signal arrives at the summer, then the negative sign on the summer inverts x sub f to become the new x sub I. If, furthermore, the loop gain caused x sub f to become negative x sub I, then the output will continue even with no input x sub s. This is known as oscillation. Oscillation occurs because the delay of the loop gain blocks is exactly 180 degrees, making the signal at x sub f upside down from the signal at x sub I. And the magnitude of the loop gain is 1, making the amplitudes the same. so that x sub I equals minus x sub f, or vice versa. If the delay of the loop gain is 180 degrees and the magnitude of the loop gain is greater than 1, then the oscillation grows exponentially over time. The frequency of oscillation is the frequency where the delay between the input and the feedback signals is exactly 180 degrees. In the real world, obtaining equality is almost impossible. So what usually happens is the oscillation grows exponentially while the amplifier is acting nearly linear. But the amplitude of the oscillation stabilizes when the peak amplitude gets close to the power supply limits. In summary, if the magnitude of the loop gain is greater than or equal to 1, and the angle is minus 180 degrees, oscillation ensues at the frequency this occurs.